So welcome all to today's tutorial. This is week 7 tutorial for the course Essential Mathematics for Machine Learning. I am Pintu Kumar. I am a PhD scholar at IUR IIT Bombay. The topics that I intend to cover can be broadly categorized as basics of calculus. I'll talk about functions. Here I'll talk about some special type of functions like even function, odd function, one and onto functions, and the like inverse function and those kind of things. Then I'll go to derivatives and limits and derivatives. Okay, then I'll go to limits and derivatives. Here I'll also talk about here I'll also talk about partial derivatives. Then I'll move to function like Jacobians, Hessian, and also talk about directional derivatives. Okay, so if you'll stick with me, then probably I'll cover questions related to what are there in assignment, and if these questions are clear to you, then most probably you will be able to solve whatever is there in the assignment. Okay, so what is a function? So for me, what I understand a function is an assignment of, so in function you have two sets. Okay, one is called domain and another one is called codomain. Okay, so what is a function? A function is an assignment, so you assign every element of your domain to some element in codomain, and this assignment should be unique. Okay, so this is the basic idea, that for every element in domain, so you should cover all the elements in domain, you should have a unique mapping to some element in codomain. Okay, so by unique mapping I mean that this same element can't be mapped to two elements at the same time, then it's not a function. Okay, so this mapping is not possible, only one mapping is possible. Okay, so if you look at this definition, so this says that if some variable y, let's say, depends on some other variable x in such a way that each value of x determines exactly one value of y, that is you have a unique mapping for each value of x. So this is the same thing that I said, then y is a function of x. Okay, so this is the idea of a function, that for every element in domain you should have a map in codomain and the mapping should be unique. Okay, so while discussing this definition, I already talked about what is a domain. So domain is the set of points which are being mapped. Okay, so domain is the left hand side, so points that are being mapped, and your codomain is the set into which this thing is getting mapped. Okay, and if you, now I said that every element of your domain should be mapped, but it is not necessary that every element of your codomain is also occupied. Okay, so there can be some elements in codomain which are actually not occupied. So if you just take a set containing all the elements in your codomains which are occupied, that set forms the range space of that function. Okay, so that is the range of that function. So let me take an example. Okay, before this, let me take a simpler example. So if you have something like f of x is equal to x square. Okay, so what is this f? This f is a mapping from R to R. Okay, so what is your domain? Your domain is your real numbers. What is your codomain? Your codomain is again a real number. Now if you look at the values that can be attained by this function, that is f of x is equal to x square, then you will realize that f of x is always greater than equal to 0, because square of any number is always greater than equal to 0, right? So that's why your range space would be something like 0 to infinity. Okay, so I hope this is clear for anybody for whom this definition of function, domain, codomain and range is not clear. Okay, so here are two examples that we are going to solve. So for both the questions, we have to find the domain and range of this these two functions that is given to us. Okay. Okay. One small thing. This is not something logical but conventional. So if you define a function like f of x is equal to square root of something, let's say x, then if you look at, like, if you remember that if you look at square root of 4, then it can attain both values plus 2 and minus 2, right? But if you write it in form of a function, then you only take the positive value that come out of this square root. This is not something logical but conventional. People follow this convention. So if you are given that f of x is equal to square root of x and you want to calculate f of 4, then its value is 2. Because for function we just want a unique mapping, right? So we can't allow minus 2. So for convention we stick to positive values that is being returned by square root. Okay. Okay. So for the first part, we are given that our f of x is 2 plus square root of x minus 1. Okay. So what is, if you want to find the domain of some function, then what you want to see is, you want to see the values for which you can find f of x. Okay, for which your f of x is well defined, right? You want to find those x. So if you look at this function, 2 won't have any problem on definition of f of x. So for 2 is defined for every value of x, right? So the problem can occur from the square root of x minus 1. So square root of x minus 1 is defined only if your x minus 1 is greater than equal to 0, right? If your value inside the square root is less than 0, then if this is a map from R to R, then it is not defined, right? So this would imply that your x should be strictly greater than equal to 1. So if you look at the domain of this function, domain is that your 1 to infinity. I hope everybody knows that this square bracket means that this value 1 is included in this set, and so if you use this curly bracket, that means that that particular, if you write something like 1 comma 2, then this 1 and 2 are not included in this set. Okay. Okay. So now if you want to find the range of this set, okay, now it is saying that if you that the only values that is allowed is like x belonging to this particular set, right? So what are the output values that we get? If we have x is equal to 1, we get f of 1 is equal to 2. So if we have now higher values of x, then you can see that this x minus 1 will gradually increase and the square root value will also increase, right? So if you have x greater than 1, not equal to x greater than 1, then f of 1 will be gradually increasing and it would be greater than equal to 2. So what is the range? The range that you obtain is 2 comma infinity. Okay. Hope this was clear. Now let's try another example for the same topic. Okay. So the b part is given to be f of x is equal to x plus 1 divided by x minus 1. Okay. So again, the same definition for domain. If you want to find domain for some function, you just want to see where your f of x is defined. Okay. So if you look at this, your f of x will be defined everywhere except of the time or except of the values of x when your denominator becomes 0. So if you have something by 0, that thing is not defined, right? So what you want, you don't want your denominator to be 0. So if you look at x minus 1 equal to 0, this implies x is equal to 1. So your domain is R minus 1. So this is everything except of 1. Okay. And what is the range of this particular function? What are the values that this can take? So if you want to calculate the range, then this is x plus 1 divided by x minus 1, right? So if you assign this thing, let's say to some c, right, then what does this mean? That your x plus 1 is equal to c times x minus 1. This would imply x 1 minus c is equal to minus of 1 minus c, right? Then this would imply that your x is equal to if you take the minus sign out, then this would be 1 plus c divided by c minus 1, right? So you can find the value of x for which your f of x is c. Okay. Now, for what value is this not defined? This is not defined when your c is equal to 1. Okay. So you can't find an x when this particular term is equal to 1. Okay. So what is your range? Range is again r minus 1. Any doubt in these two parts? Okay, so if anybody has any doubt, you can either type it into the chat box or you can unmute yourself to ask the question.
So this procedure is always possible.
Which procedure?
Finding range.
So you can find the range of any function. That might not be as easy as this question, but yeah, you can look at the points what you can have. Yeah, you can find the range always. Okay. Okay, so this question I'll not do. Here are 4 examples. If you want to just, if somebody wants to practice, that's why I included. So you have to find the domain of these questions. Okay, so this is not very difficult, right? Again, here you will have some 2 points in B part, and D part also you'll have 2 points. In tan x you have to look what values are going to 0. So are not defined and those kind of things. Okay. Okay. So now I would talk about some special kind of functions. Okay. So like in many lectures we talked about identity of a vector space and those kind of things. Now if you look at function, what is an identity function? So identity function is nothing but a function which returns itself. So if your f of x is equal to x, this particular function is called the identity function. Okay. Now another important function is something that is called inverse function, and this inverse function might not always exist for every function. There are some special type of functions for which your inverse function exists. Okay. So what is an inverse function? Let's say if f is a function from let's stick to r to r right now. Okay, you can extend it accordingly. Then f inverse is also a function from r. Let's say this is rn to rm. Then f inverse is a function from rm to rn. So such that f of f inverse. So let me write it another way. So this is f inverse of f of x is equal to x. Okay. So if you take the map from Rn to Rm and then you again take the inverse, then you should get back the same element, and this is true for all x. Then your f inverse is called inverse of f. and this should be true both ways. So it should also be that f of f inverse of x is equal to x. Okay, so this is the definition of inverse function. Okay. Okay. So now we'll come to something that is called as odd function or even function. So let's look at the definition of even function first. So f is called an even function if f of minus x is equal to f of x. So even if you input the value with a negative sign, then you will get the same function. Okay. So if you look at it geometrically, what it means that it should be symmetrical. Sorry, it's like if you have, yeah, it should be symmetrical about the y-axis. So whatever values you have on the this right hand side, let's say on the right hand side you have, just give me a second. If you have this purple curve, then on the left hand side it should be just the mirror image of the same thing, right? Because f of minus x is nothing but f of x. Okay. So looking at some of the examples, one of the easiest example is f of x is equal to x square. So even if you take f of minus x, this is minus x whole square, which is equal to x square. Okay. Another example is cos x. So cos of minus x is nothing but cos x, right? So this is another example of an even function. Now the opposite of even function is something that is called as odd function. So what is an odd function? F is called an odd function if f of minus x is equal to minus of f of x. Okay. So the negative sign, if that comes out of the function, then that particular function is called as the odd function, right? So if you look at some of the examples, then you can just take the simplest example to be f of x is equal to x or x cube and so on. And from the trigonometric functions, you can take sine x or tan x, right? These kind of functions are odd functions. Okay. Okay. Now, what is an 1 function and onto function? So, as I mentioned initially when defining function, function is nothing but a map from domain to codomain, right? So, let's say your codomain have some points and domain have some points. Yeah. So what I said is that for a function to exist, every point on your left hand side, that is your domain, must be mapped to some point on the right hand side, that is your codomain, right? But also I said that the mapping should be unique, that any element of the left hand side should not be mapped to two elements on the right hand side, right? But I didn't said anything about what is the condition on right hand side. Okay, so if you look at this particular mapping, this is a perfectly defined function, this is a well defined function, right? Now if you impose an extra condition that every element on the right hand side should also be uniquely mapped to an element on left hand side, so now every element on right hand side has only one pre-image. So if you look backwards, that is something that is called as pre-image, it has unique pre-image. then this kind of function is called as an 1-1 function. Okay. So graphically, how you can know that a function is 1-1? So let's say if you have some graph of a function and you draw a line parallel to x-axis at any point, then it should intersect only one point, right? So if you draw any line parallel to x-axis, then it should only cut one point on your graph. Then that kind of functions are 1-1 function. So if you look at another example, so let's say your function is something like this. Yeah, this is x is something like x square, not a perfect graph. So now if you draw any point line parallel to your x-axis, you see that this line cuts this graph at 2 points. So this particular example is not a 1-1 function. Okay. So I'll just include one more comment. So if somebody gives you some function and wants you to prove that that particular function is a 1-1, what is the approach you should take? So let's say you are given with some f of x and you have to prove that f is 1-1, then what you should do is, so you should assume that let's say some f of x1 is equal to f of x2. And then by some calculation, you should reach to a point that x1 is equal to x2. What does this mean? This means that whenever your f of x1 and f of x2 are same, then it must happen that your x1 and x2 are indeed the same values. Then that's when your function is 1-1. Okay. So if somebody asks you to prove, then you should assume this thing, and using computation, you should reach to the point that your x1 is equal to x2. Okay. Now let's go to onto functions. Let me copy this diagram. Okay, and let me erase the later line that I drew. Yeah. So let's say this point is still mapped to this point. Then you can see on the right hand side in your codomain, you have an empty point that does not have a pre-image. Okay. So if you impose an extra condition on your function that every element on your right hand side should be occupied. Okay, let's say you have one more point here and this is also mapped to this point. Okay, so this kind of function in which your every element on the right hand side has a pre-image, then those kind of function are called onto functions. Okay, so this function is not 1-1 because this last element has two pre-images, but this is an onto function because every element is occupied. Okay. And the last definition is for a bijective function. Bijective function is nothing but a function which is 1-1 plus onto. Okay. So if a function is both 1-1 as well as onto, those kind of function are called bijective function, and their property is that if a function is bijective function, then the inverse for that particular function exists. Okay. So you can invert that function. So we talked about invertible function. What is an inverse of a function? So if a function is a bijective function, then only it can have an inverse. Okay. Any doubts till now about the basics of function and whatever we have discussed till now? Okay. Okay. So now let's come to limits. Okay. So first of all, let's try to understand why limits are important, right? So we can find exact value of some function at some point. Okay. We can do exact computation, but still why do we need limits, right? So there are two motivations that I found useful. First one is that, let's say you have some curve, let's say this is your curve, and at this point you want to draw a tangent, right? Or you want to find slope of this particular tangent. Okay, then how can you find, right? One question is this. So one approach that you can take is, you take these 2 points, okay, and draw a line connecting these 2 points. So something similar to what they have done here. So they have taken these 2 points initially, right, and they have drew a line passing through these 2 points, okay, and then they captured the slope of this particular line. Then what they did is, they reduced the distance between these 2 points. The next time they took a closer point, right, and then they calculated the slope of that particular line. Then again they made the point closer and then calculated the slope. So if you keep getting closer to this particular point, so if you keep taking points closer to this, eventually what you will get is, you will get the slope of this tangent line, right? So that's why when the slope is not explicitly calculatable, so you can't calculate it explicitly, then what you do is, you approach it via limits. Okay, so you keep coming closer to P and calculating the slope of the lines, and you will eventually find the slope of the tangent. Okay, so this is one motivation. And second motivation is, so this first motivation later on turned out to be the area of differentiation that you might have studied in class 12. So this is the like the core idea behind your differentiation. Okay, so this example is this example actually motivated integration. So the problem at hand is that you want to find the area between A to B that is under this sky blue curve. Okay, so you want to find this particular area. So one way to do that is, so you know what is the area of a rectangle, right? So this height would be f of A, right, and this width you have fixed beforehand. Okay, so you know the area of this rectangle. So what you can do is, at some distance you can measure the height, draw these kinds of rectangle, calculate their area and sum it up, right? But you see there is a lot of error in this estimation. You see error over here and so on. So if you now make your rectangles more finer, then you get a better estimate. Now if you limit the width of this rectangle to 0, then you can get a perfect fit with 0 error, right? So this is the idea behind your integration. So to measure quantity that you study in your calculus, that is integration and differentiation, both evolved out of the idea of limits. Okay, so that's why studying limits is important. So what actually the limit is for a function? So let's say, just give me a minute. Okay, let's say this is some curve, right? This is some function. Okay, so and this is some point A. Okay, so in limit, what you want to do is, you are not interested in value of function at point A. Okay, but what you want to do is, you want to see if I'm very close to A, right? If I am, let's say, from here to here, this green thing that I drew, if I'm very close to A, what is the value of function? Okay, so now for the limit to be defined, if you see, sorry, you can reach A from two sides, right? You can reach A from right hand side and see how values are going and where you are limiting to, and you will get some value that is called as a right hand limit. Similarly, if you now come from the left hand side, then again you will get some limit for a. So if you are on just left to the a, you will have some value that is called as your left hand limit. And if both this left hand limit and right hand limit are equal, then we say that the limit exists at a. Okay, so then your value of limit, so if you are very close to a, then you are certain that you will have some value for that function. Okay, so this is the idea behind limit. Okay, now we have these three questions that we have to solve. Now if you look at this particular first example, if you are very close to uh, 3, then your denominator is becoming 0, right? So because you are very close to 3, then x minus 3 will be very close to 0 and this limit won't exist, then the value will explode. So how to deal these kind of questions is, so generally you will have some other term on the top which will generally split and cancel out the denominator term. Okay, so if you look at the first example, so this is x square minus 6x plus 9 divided by x minus 3. If you just break the above term, this would be minus 3x plus 9 divided by x minus 3. So you can take x common, and yeah, this is minus 3, x minus 3 divided by x minus 3. So this is x minus 3 whole square divided by x minus 3. Now if you cancel out these two, you will get x minus 3. So rather than calculating this limit, you can just restrict it to limit x tends to 3, x minus 3, and this value is 0. Yeah, you have some doubt, you can speak. Somebody raised hand. Okay, I think that was by mistake. So let's look at another example. So the B part is limit x tends to minus 4. This is 2x plus 8 divided by x square plus x minus 12. Now again, if you directly put the value of 4, okay, then what will happen is the denominator is 16 minus 4 minus 12. The denominator will become 0 and hence this limit won't be defined. Okay, so again we want to split the higher order term. So the first term is just a polynomial on the top. In the denominator you have now a degree 2 polynomial. So we will try to split the second term. So the top term is 2x plus 8, okay, divided by x square plus 4x minus 3x minus 12, and this is 2. If you take common x plus 4, in the denominator you will be left with x plus 4 minus 3, x plus 4. So you can cancel out x plus 4 and you will left with 2 upon x minus 3. So rather than calculating limit on the earlier thing, you can just calculate limit here, 2 upon x minus 3, and this is 2 upon minus 4 minus 3, this is minus 2 upon 7. So this is the way to approach these kind of questions, and similarly you can solve the C part also. It is quite similar. We just need to split both of them and you will get the same thing. Okay, so yes, okay, okay. So what is meant by continuity? So a function, if you vaguely speak, is continuous if you can draw its graph without lifting the pen. Okay, so what is meant when you say that you can draw the graph without lifting the pen? That means that if you are at this point, the value at very next point would be close to the value at that particular point. So let's say if this is f of x, then at some point x plus h, where h is very small, then f of x plus h will be close to f of x. That's why you are able to reach there without lifting your pen, right? So let's say if the graph was something like this, yeah, so there is a sudden jump in value of uh, f of x at this point, so you can't draw this without lifting the pen, right? So what you want is that the values in vicinity of your f of x, so at nearby points, should be close to f of x, right? So this idea is captured by a definition. So you say that a function is continuous at point a if limit exists at a. First point is that if you are approaching this point either from left hand side or from right hand side, you should reach the same value. Here what is happening, that you are ending up at different points, right? So you should reach the same point. Okay, let's draw one more graph on the similar lines. Let's say this, and just at this point your value is this much, and other point you are continuously flowing. So if you look at the limit, this is also suggesting that you are approaching this point, this is also suggesting that you are approaching this point, but the function value is here, so you can't draw this without lifting the pen, right? So the second point that we have is that f of a should be equal to limit x tends to a f of x. First thing is that this limit should have existed, and this limit should be equal to the function value at that point. Okay, if these two conditions are satisfied, then f is said to be continuous at a. Okay, this is simple definition of continuity. Okay. Okay. Before defining derivative, let's see what is meant by a function being differentiable. Okay. So again, I'll draw this graph only, right? So let's say I have some curve. Let's say I have some graph. I want to look if my function is differentiable at this point or not. Okay. Let's say this is point A. Then what is meant by differentiability is, so what is meant by differentiability is that the slope of the tangent must be, there should be a, first of all, there should be a unique tangent at that point, right? And the slope should be defined for that particular tangent. Okay. So if you are able to find the tangent at a point, then the function is differentiable at that point. Okay. So let's take an example which is not actually differentiable. Then you'll understand why this thing is important. Let's say you have modulus function. So this is your modulus function that I have drawn with orange color. Okay. So if you look at this point, then there are many tangents that can be drawn. This purple line is a tangent. Now what I have drawn is a tangent. Now what I have drawn is a tangent. So there is no unique tangent at this point. That's why we say that this function is not differentiable at this point. Okay. So just to inspire the definition of right, this derivative. So when do we have a unique tangent? So let's say we want to find a tangent at this point A. If you look at the motivation for limit, what we used to do is, from here we used to draw a line and then look at its slope, and then we kept pushing this point P closer to A. Okay, this was the idea, right? And similarly, we will do it from this side also. So we will have some point Q, we will draw a line between Q and A, look at its slope, and then keep pushing Q as close as possible to A, and then we should have a slope of this tangent, right? Now, when would this be differentiable? If I am pushing from right hand side or if I am pushing from left hand side, both these values should match, then only my function is differentiable. Okay. So this is the definition. So if you look at this point P, let's say this is, so this particular point is X and this is C, right? Then what is this slope? The slope is y2 minus y1 upon x2 minus x1, right? Then slope is f of x minus f of c upon divided by x minus c, right? And if I send my limit x tends to c, that means I am coming from right hand side also and I am coming from left hand side also. And if this exists, then that is called the differentiation or the derivative of f at point x. Okay, at point c, sorry. Yeah. Okay. So this is the idea behind derivative. So this is better explained here via this figure. So if you look at this point P and this is Q, then the slope is given by f of x minus x naught divided by x minus x naught, and you will push this point Q close to P, right? And that's why we take limit x tends to x naught, or in our case x tends to c. Okay, so this derivative, I think almost all of you know how to calculate derivative of some function. You have been doing it since class 11th, right? So I won't solve questions based on derivative, but rather we can solve some questions based on partial derivative and those kind of things. Okay. Now we come to partial derivative. Before going to partial derivative, it's 6:51. It's a long 2-hour class, so let's take a break for let's say 4 minutes, and I'll start at 6:55. Till that time, if anybody has any doubt in whatever we have covered till now, you can ask, please. Otherwise, we'll start in 4 minutes. That is at 6:55. So till now, whatever plots I drew while discussing limits or continuity or differentiability, you can see that all those functions were from real number to real number, right? Now, you have many kinds of function, right? Especially if you are dealing with machine learning and those kind of things. Then there is a possibility that you have a function from some Rn to R. Okay, so if you look at your loss function uh, in your machine learning, so loss functions are generally a map from Rn to R, right, where your n is your number of features. Okay, right. So you here are also sort of incorporating the f inside the loss function only. Okay, what your loss function here is doing, it is taking just the raw features and then finding the loss on that, right? Okay, so let's say you have a function of two variables x comma y. Okay, something like, let's say, x square plus 2xy. Okay, now when you were taking derivative, initially you had only one dependent variable and one independent variable, so you used to take a derivative of independent variable with respect to your dependent variables. But now you have two independent variables, right? And you have this dependent uh, expression. So there is a possibility that you can take derivative with respect to uh, any of your independent variable, right? So what you can do is you can find derivative of f with respect to x, as well as you can find derivative of f with respect to y. Okay, but now because you are treating the other thing, that your x as some constant, you replace this straight d by this tilde d, and this is called del. Okay, so this is del f by del x and this is del f by del y. Okay, so this denotes partial derivative. Okay, so what is partial derivative? So earlier what you used to do is that was f of x minus f of c divided by x minus c, right? Now because you are changing only in the direction of x, okay, so this is defined as f of x plus delta x, y naught is fixed as a constant, f of x naught comma y naught divided by the change, that is your change in so from x naught to delta x minus x naught, you will get delta x. Okay, this is similar to x minus c. So this is your derivative with respect to x and this is your derivative with respect to y. Okay, so this is how your partial derivative is defined. In reality, if you want to just find the partial derivative, let's say your f of x y is something similar to what we wrote. Let's say this is x square plus 2xy, and you want to find del f by del x, for example. Then what you should do is you should treat your y term as a constant term. Okay, so similar to your normal differentiation, you should calculate treating other terms as your constant term. So if you look at this, this would be 2x. Now treating y as constant, 2y into del x by dx by dx is 1, right? So this is 2x plus 2y. Similarly, if you want to calculate f of y, this is another notation for your partial derivative. So the first term is 0 because this is a constant for y, and the second term is 2x. So f of y is 2x. Okay, this is how you calculate. Okay. Now, I think most of you must be aware about quotient rule for differentiation. That is, if you take derivative of f of x by g of x, then this is nothing but f dash x, that is derivative of x into gx minus derivative of g into f of x divided by g of x whole square. Okay. So now we have a question at our hand, okay, where we want to show that my f of x that is partial derivative of f with respect to x and partial derivative of f with respect to y exist at all points, and we also need to explain that why this f is not continuous. Okay. So we need to explain this thing. Okay. Okay. So let's look at this thing and let's try to find f of x. Okay. So for f of x, what is the value? If you use the quotient rule, so your quotient rule says, let's say my x and y right now are not equal to 0. Okay. For other cases. Okay. So let's see what happens over here. So this derivative would be, so now I have to treat y as a constant. Okay. So the derivative of the top part with respect to x, that is y into x square plus y square, and there is a minus sign ahead of it, right? Now again a minus, just give me a second. So this is minus in front of everything. Okay. So derivative of the bottom part with respect to x, so this is 2x plus this y square becomes 0, so this is 2x into minus xy. We have already taken this minus sign here, so this is xy divided by x square plus y square whole square. Okay. So what is this value? This is this would be y times x square plus y square minus 2x square y, right, divided by x square plus y square whole square, right. This is when your both x and y are not equal to 0. Then you can use this formula because you have this thing getting to 0 in the denominator. So we need to explicitly check for x, y is equal to 0 whether this differentiation exists or not, and if it does exist, what is the value. Okay, so there is a similar question in your assignment where you have some terms in the numerator and some terms in the denominator, and you have to find the partial derivative. Okay, so we will try to find f of x. Okay, and similarly you can attempt for f of y. Okay, so what is f of x? At 0 comma 0 we want to find. Okay, so this would be limit delta x tends to 0, just using the definition. This is 0 plus delta x, okay, comma 0 minus f of 0 comma 0 divided by delta x, right. So what is f of 0 plus delta x comma 0? Because delta x is a non-zero value, it is close to 0 but a non-zero value, right. So its value will be this particular expression that we have. Okay. Now the y term, y is 0 over here, so this would be delta, okay, let me write it down. So this would be delta x into 0 divided by delta x square plus 0 square. F of 0, 0 is anyway 0 divided by delta x. So what is this value? This is 0 minus 0 divided by delta x, which is nothing but 0, right. So f of x is defined even at 0 comma 0, and for other values we have already found it out. Similarly, you can attempt finding f of y, and so if you are able to find it, then this proves that this thing exists for all points x and y. Okay. Okay, second part I wanted to do especially. Okay. Okay. I would just want you to just focus a bit right now. So let's say when we had a plot like this, okay, when you had a f of x, let's say, okay, let's say this is my plot. Whenever you used to look for the continuity or the limit of this function, let's say at this point a, Then to approach this particular point, let's say this is x and you get a as f of x. Okay. Now to approach this point x, you have two ways. That is, you can approach it from right, where we used to calculate right hand limit. Okay. And you had another part to approach, which was your left hand limit, right? So there were only two ways to reach x. That's why we just used to check whether our left hand limit is equal to right hand limit or not. Okay. Now let's say you have a 3D function. Okay. And let's say, uh, let's me try to draw. I'm not very good at drawing, but I'll try to. Okay. So let's say there is a some 3D function. Okay. This is some 3D function. And you want to check its limit at, let's say, this point 0 comma 0 comma 0. Okay, so this is my 0 comma 0 comma 0. So this is a function of, this is x axis and y axis, right? So this is a function of x and y, this complete plane, and its value lies in the z axis, right? So now in your xy plane, there are, what I want to point out is, there are, let's say you want to approach your 0 comma 0 via this purple line that I just drew. Another possibility is that you want to approach there by this particular line that I'm drawing. Okay, you can come from this side also. Okay, you can come via some curve, more curvy lines, right? So what I'm trying to say is, when you want to check the continuity or limit of a multivariate function where you have more than one independent variable, then you have to check the limit from all the directions that are possible to reach 0 comma 0. So there are infinitely many directions, right? So the task is not that easy, but yeah, so when you want to check, the rule is that you have to see it from all the directions that is possible. Okay, this is just what I wanted to say. Okay, so now let's look at the example that was mentioned to us. So let me push everything down. Yeah, perfect. Okay, so for this equation, uh, so I have to check the continuity at 0 comma 0, right? To reach 0 comma 0, let me take two lines, right? One is y is equal to x. So if you look at line y is equal to x, this passes through point 0 comma 0. Okay, and let me take point y is equal to 2x. Okay, these are my two paths. Okay, and let's see if I approach 0 comma 0 via these two paths, whether I get same limit of this function or not. So if my limit don't exist at all, then there is no point of talking about continuity. Okay, so let's say if I want to approach my y via this line y is equal to x, so what is function value? So f of 0 comma 0, I want to calculate at f of 0 comma 0. Okay, so this, so let me use some better notation. So this is limit y tends to x, f of xy, and we want to calculate it at 0 comma 0. Okay, remember that. So this would be minus x square divided by x square plus y square. What it is? So this will be again x square. So this is minus 1 upon 2, right? So if I'm approaching my point 0 comma 0 along this line y is equal to x, okay, then at point 0 comma 0 the function value is tending to minus 1 by 2. Okay, and let's look at other one, which is limit y tends to 2x at 0 comma 0 f of xy. This is minus x into 2x divided by x square plus 4x square. So this is again minus 2x square by 5x square. So this is minus 2 by 5. So now you see, if I approach point 0 comma 0 via these two different lines which are passing through 0 comma 0, then I am getting different values. What does this mean? That the limit for f does not exist at 0 comma 0. That's why this is not continuous. Okay. Any doubt in this question? Okay. So these are some examples that I want to solve related to second order partial differential equation. So what we have to find is, in this question we have to find, yeah.
Sir, please explain previous.
Okay, what didn't you understand in previous question? Can you please be yeah.
Continue.
Hmm.
And application of formula.
Acha. So this part you didn't understood. Okay, so I hope you didn't understood this part. So here what we did is, we were going through the line y is equal to x. Okay, so we just replace y everywhere with x. So the top term became x minus x square. Here again it became x square plus x square. So on the top we have 1x square, on the bottom we have 2x square, so this became minus 1 by 2. Okay, the next time we approached via line y tends to 2x. Okay, so y was replaced by 2x and the denominator became 4x square. So on the top we have minus 2x square, on the bottom we have 5x square. So the value that we obtain at the end is minus 2 by 5. Okay, so because these values are not equal, so the limit at limit x comma y tends to 0 comma 0, f of x does not exist. Is this clear
Sir,
now? Yeah.
sir, if we take path y tends to x by 2,
Mm-hmm. Then again we will get some other value, right?
sir, I think we are getting again minus 2 by 5.
That's fine, but so you, like,
So
if you
basically,
have
we have to check for multiple values.
so in case you want to prove something, it is that the limit does not exist or is not continuous, then you have to find two paths where you get different values. So sometimes there would be a possibility where all straight lines would be converging to same point, that is, their limit will be same point, but some quadratic function will, if you approach via some quadratic function, then the value will be different. So those kind of possibilities are also there, but this won't be very much useful. So this is to just know that when you are checking the limit, you should check from all the directions, but this won't be very useful in machine learning. That's why I just included one example just to give you the concept. But if you want to practice, you can see any calculus book. There are a lot of examples where you approach via different paths. Okay, so you approach via quadratic paths and those kind of things. If you want a book, you can view calculus by Anton and Davis. This is also a good book. This is a very elementary, and you have many examples also there, so you can have a look if you are interested, but this won't be very useful for your machine learning applications. Okay. Okay. So now we want to calculate the second order partial derivative, that is f of xx, f of xy, f of yx, f of yy. I haven't defined these terms. What is f of xx? So first of all, let's see what is f of x. F of x is del f by del x, partial derivative with respect to x. Okay. What is fy? This is partial derivative of f with respect to y. What is f of xx? This is partial derivative of del f by del x. So you have calculated derivative once, partial derivative, you are again calculating its partial derivative with respect to x. What is f of xy? This is partial derivative of del f by del x. So whatever comes first is evaluated first, whatever comes last is evaluated later. Okay. So now let's look at this particular example. We want to find all the second order derivatives. So first begin with first order derivative. So what is f of x for this? We will treat y as constants. Then the first term is 2x into y cube because y is treated as constant. And the second term is 4x cube y. Okay. What is my f of y? Now we'll treat x as constant. So this will be 3y square x square plus x to the power 4 because the derivative of y is 1. Okay. Now let's calculate the second order derivatives. What is f of xx? We will calculate partial derivative of this particular term with respect to x. Okay. So this particular term with respect to x, and we will obtain 2y cube plus 8, sorry, it would be 12, not 8, plus 4 3s are 12 x square y. Okay. Now let's calculate f of xy. So now we want to calculate the derivative of this thing with respect to y. What it is? This is 6xy square plus 4x cube. Okay. And again, we can calculate f of yx, which is your again 6xy square plus 4x cube from here. Okay. And f of yy can be calculated as 6yx square plus 0. Okay. So this is simple, right? Let's do one more example if I have included it. So this is f of xy and we want to calculate f of xyy. So first we will calculate f of x, which is treating y square as constant. This is y square e to the power x plus 0. Okay. Now what is f of xy? Now we will differentiate with respect to y. This is 2y to the power x. Now f of x y is differentiating this term with respect to y. This is 2 e to the power x. Okay, simple. Okay. Okay. Now we'll do something about chain rule. Any doubt till now before move on to chain rule? Okay. So let's say you have some function f, okay, which is a function of x and y. Okay. And you also know that your x indeed is function of some other independent variable t, and y is also some function of y of t. Now if you want to find the derivative of f, or in this case they have used notation z, with respect to your t, then what you can do is, so this f is dependent on two things. So first of all write those two things. So this will be del f by del x plus this will be del f by del y. Now this y again is dependent on t, right? So you will include, sorry, the x is dependent on t, so we will include another term, that is dx by dt. Okay. If you look carefully, this would be something like this, and these terms get cancelled and something like that, but yeah, that is just to visualize, and this will be dy by dt. Okay. So if you had more terms in f, let's say this was x, y, w, then you would have another term, that is df by dw and dw by dt. Okay. So let's try to solve this example. It says that we have to find del z by dt using two methods. Okay, so one method is that, let's say this is given that your z is x square, z is x square y, right, and x is given to be t square and y is given to be t cube, right? So you can replace the value of x and y from here and you can obtain that your z is t square square into t cube, that is t to the power 7, right? So what is now dz by dt? This is 7t to the power 6. This is one way. Another way is via the chain rule that we discussed. So let's see if we get the same answer. Now del z by del t is, this is del z by del x into dx by dt, right, plus del z by del y into dy by dt. So what is del z by del x? You will get 2 x y, and what is del x by dt? This is 2t, right? Now this is plus, what is del z by, this is x square into 3t square. Okay, now let's replace the value of x and y. What we will get is, this is 2xy, so this is 2t to the power 5 into 2t plus x square is t to the power 4, right, t to the power 4 into 3t square, right, this is 4 t to the power 6 plus 3 t to the power 6, that is 7 t to the power 6. We get the same answer. Now you will say, why this much calculation when we can directly evaluate? So that becomes useful when your x and y are again functions of more than one variable, that we'll see right now. Yeah, for example in this particular question. Okay, so let's say now your z is a function of x and y, and x is again some function of u and v, and y is also some function of u and v. Okay, then if you want to calculate the partial derivative of z with respect to u, what you can do is you can just go step by step. So z is a function of x and y, so you split it into two branches. So this would be del z by del x plus del z by del y. Now what is to be multiplied here? So you will multiply it with del x by del u, because x is again function of two variables u and v, right, but we are interested in this branch u wala, right? So again this would be del y by del u. Okay, so this is how you will find. So let's look at this example. So we have to find del z by del u, which is uh, del z by del x into del x by del u plus del z by del y into del y by del u. Okay, so this is equal to, this is e to the power xy, we will treat y as a constant, right? So what will be obtained? So e to the power xy remains as it is. Now again we go to the top, so we get y e to the power xy, right? And what is the derivative with respect to u for this particular thing? This is 2, right? Now again we will get x e to the power xy, and the derivative of this with respect to u is just 1 by v. So the value that we get is 2, let's take e to the power xy common, so this is 2y plus x by v. Okay, now you can replace the value of x and y in terms of u and v, and you will get del z by del u in terms of u and v, right? So you can get e to the power 2u plus v into u by v. You can expand it, and this is 2u by v plus 2u plus v by v, and again you can merge these things. Okay, so this is how you go about chain rule, right? So yeah, similarly you can find when you have three variables too. So w is a function of x, y and z now. So del w by del u would be nothing but del w by del x into del x by del u plus del w by del y into del y by del u plus del w by, somebody has joined, let me admit that person. Yeah. Okay, and del w by del z into del z by del u, right? So you can calculate these values and then evaluate, right? Okay. Okay. So till now, what we have done, we have talked about partial derivative, right? If you look at the definition of partial derivative, it was limit delta x tends to 0, f of x plus delta x comma y minus f of x comma y divided by delta x, right? Yeah, this was your formula for partial derivative. Okay, so now if you look at this thing, what this thing is suggesting is that in x direction of this function, okay, so this function is a function of x and y. So in x direction you are incrementing a bit and you are seeing how much change in function you are getting with respect to the change that you are making in x direction. So this partial derivative with respect to x is giving you the rate of change with respect to change in your x direction. Similarly, your f of y would give you the change in function, the perturbation in function, if you change your y a little bit, right? Now the question is, if you want to see or observe the change in function with respect to some arbitrary direction u, okay, what you want to do is, you want to see if I move a little bit in direction of u, how much my function varies. Okay, so it's yeah, so it is simple and it is given by this particular formula. Okay, so if you move in direction of u, where u is your some unit vector, okay, then the directional derivative in direction of u at some point x naught comma y naught is given by, first of all you will incorporate a fictitious variable s, okay, and this is given by f of x naught plus su1 comma y plus su2 at s equal to 0. So if you want to look at this thing in terms of definition we have been talking till now, so this is f of x plus su1 comma y plus su2 minus f of x y divided by s, and your s tends to 0. So this is what is meant by directional derivative. Okay, so just remember this formula. We have an example we'll solve, and there is a question in assignment that you can solve very similarly. So here we have been given that my vector is a unit vector. If you are given with some vector which is not a unit vector, then first task would be to convert it into a unit vector. Okay. So what is this thing? Directional derivative in this direction at point 1 comma 2 we have to find. So what was given, that it is d by ds of f of x, here is 1, right? So this is 1 plus, this is u1 times of s. Okay, so the u1 over here is this root 3 by 2s. Okay, and y is 2 plus 1 by 2s. Okay, now the derivative of this at s equal to 0. Okay, so let's calculate what is f of this value. F of xy is given by x into y. So this is d by ds of 1 plus root 3 by 2s into 2 plus 1 by 2 of s. Okay, and then we have to calculate it at s is equal to 0, right? So let's multiply the inner part, then we will have d by ds of something which is, let's say this is 2, now this is root 3s, right? I multiplied these two terms with 2, right? Now let's go the other way around. So this is plus 1 by 2s, and the last term is plus 3 root 3 by 4 s square, and at s equal to 0. Okay, so what is its differentiation with respect to s? This is, first term becomes 0, second term is root 3 plus 1 by 2 plus root 3 by 2s, right, at s equal to 0. Now if we put the value of s equal to 0, what we obtain is root 3 plus 1 by 2. So the directional derivative of this function in this direction is root 3 plus 1 by 2 at 1 comma 2. Somebody raised their hand in between. Can you please?
Sir, why we can multiply?
Because my f of xy is given to be x into y. So what was the formula?
There is a multiplication.
Yeah, because my f of x y says that you multiply x and y. So I wanted to
Okay.
calculate x of f of x plus s u1 and y of s u2. So if my f of x y is x multiplied by y, so this is simply x naught plus s u1 into y naught plus s u2. So this will depend on the function that is given to you. Okay, so based on that you have to do this. You have to calculate f of this term and then take its derivative with respect to s and then put s equal to 0. Okay. Okay. Now, can you please mute yourself? Okay. Now we'll come to something called gradient, which is quite important from machine learning perspective, and you would have also seen this till now. So the gradient is defined as, so let's say you have a function from Rn to R. Okay, so the gradient is defined as, so del f by del x1, del f by del x2, and so on till del f by del xn. So this is how your gradient is defined. Okay, now there are two very important properties of gradient, okay, that I'm not going to prove but I'm going to state. First of all, I said that whenever you calculate the directional derivative, it gives you the change in function if you move a little bit. Okay, so there would be, let's say you are moving in u1 direction by some 1 unit, okay, and in u2 direction by 1 unit. you observe change C1 over here and you observe change C2 over here, then there must be some direction in which this change is maximum. Okay, the function is increasing maximum if you are moving in that direction. That direction is given by the gradient. Okay, so the gradient is also called the direction of steepest ascent. Okay, so steepest ascent, that is the function is increasing maximum if you are moving in this direction from a particular point. Okay, so if you calculate see the negative direction of this is known as the descent direction. So in the negative direction of your gradient, your function is decreasing at the highest rate. So if you move in the opposite direction, your function is decreasing at a rapid rate. Okay, so how is it applicable in machine learning? So if you look at the deep learning models or your complex machine learning models where loss function is quite complex, okay, and you can't use very high-end optimization techniques like Newton methods where you have to calculate the Hessian inverse and those kind of things. So where you want your optimization thing to be simple, there you use this gradient descent method. So you are at some weight, there you calculate the loss and then you move in the direction of opposite of your gradient for your loss function to reach some other point. Then again you calculate the gradient and move in the opposite direction, and so on you try to converge to your minimum loss that is possible. Okay. So this is the first point that I wanted to mention about gradients. Second point is, if you know the gradient, then you can find the directional derivative by taking the dot product of gradient with the direction. So this formula is straightforward. So you need not do all those things. You just calculate the gradient at that point. You look at the direction. This should be a unit vector again, and then you just take the dot product, and you will get the directional derivative. Okay. So I think we can try that thing also to check whether we have got the correct answer in the previous case or not. So if we look at this f of xy, what is gradient of f? So we will treat y as constant. So this becomes y and this is x, right? So this is my gradient, that is yx. Okay. And what is my u? U is this. So what is the value of y over here? So my gradient of f at this point is 2, 1. And if I take its dot product with root 3 by 2 and 1 by 2, I'll get root 3 plus 1 by 2. And this is what we get after this calculation also. Okay. Okay. So this was gradient. Okay. Now we come to something called Jacobian. Till now, whatever functions we have seen, okay, so those functions were even if my domain was a higher dimension space, but my range were always R. Okay, but that is not always the case. So let's say now your range is also some Rm, then you define a quantity called Jacobian. So let's say this is your f, then your f of x1, x2, xn will be mapped to something like this, f1, f2, fm. Then you write Jacobian in this form, that your first row is gradient of f1. Okay, so this is derivative of f1 with respect to x1, then this would be derivative of f1 with respect to x2, and so on till derivative of f1 with respect to xn. And similarly your second row is again derivative of f2 with respect to x1, okay, and so on. And your last row would be derivative of fm with respect to x1, and similarly you can proceed forming a Jacobian matrix. Okay. So here we are given with some function. Okay. So this is a function from R2 to R2. Okay. So this is a function from Q is a function from xy to some space in u comma v, which is xy comma x square plus y square. So this u, this is u and this is v. Okay, and we want to find the trace of this Jacobian. Trace is nothing but the sum of the diagonal elements. Okay, so let's find the Jacobian first. So Jacobian would be my del u by del x, then del u by del y. This would be del v by del x. This will be del v by del y, right? So let's look at, this is by x, so this would be y. So now del u by del y by would be just x, del v by del x would be 2x, del v by dy will be just 2y. Now let's put the values. So this would be 1, 1, 2, 2, and what is the trace? This is 1 plus 2, which is given by 3. Okay. So if you have a similar question, you can attempt it in a similar way. Okay. Any doubt till this point?
Any doubt till this point?
Sir, can you scroll to the formula?
Of Jacobian?
Of Jacobian?
Yes, sir.
Okay. So this formula, I think,
So
even
this
if you
formula,
look
I
at
think,
the lecture slides, there also it is more clearly written via LaTeX. So I'm just scribbling it, so you can note, but you can find a more clearer form. Somebody wrote something, or somebody?
So where we can take a transpose of gradient f.
So that is just a symbolic representation. So we just want to work with column vector, but you just need to know that it is a vector. Okay, so
So please scroll the screen
please.
of that question.
Okay. This gradient one. Yeah.
Yes, sir, it's all the example
Mm-hmm.
which will be tally.
Yeah, this one.
Sir, here is not possible
What
to
is
cross.
to multiply? I have written a dot over here. So this is dot product between two vectors.
Okay, we have to take a dot product.
This is dot product between these two vectors. This is not multiplication, but dot product.
Yes, sir, clear.
Okay. Okay. Now the last thing that is left is something called as Hessian. Okay. Hessian is sort of important tool in optimization. So you might not realize it in this lecture, but this is sort of a very important tool in optimization. So if you remember, most of you would have read class 11th and 12th maths. So there was a problem where you need to find the maximum or the minimum point of some function. Okay. So what you used to do is, let's say f is my function, then you used to calculate f dash x and put it equal to 0 to find the probable candidates for maximum and minimum. And how you used to decide whether a point is maximum or minimum? That you used to do based on the sign of double derivative, right? So double derivative was important on deciding whether your point is a maximum point or a minimum point or a saddle point sort of thing, right? So the gradient of f is equivalent to the first derivative of your function if your function is from Rn to R. Okay, so it is a multidimensional function, multivariate function. Hessian is equivalent to f double dash. Okay, so how do you construct the Hessian matrix? So first of all, let's begin with a gradient of f. So your gradient of f was given by, so you took derivative with respect to every variable. Okay, so then you took with respect to x2, then you took with respect to x3, right? Let's write it in column form only, which that would be more intuitive. Okay, then you took with respect to x2 and so on. Now you want to take the double derivative. Now what you will do is, for the first element, you will again take its derivative with respect to every variable, okay, and write it as your first row. So for the Hessian matrix, your first row becomes del f by del of x1 square. So this is del square. So you are again differentiating it with respect to x1 for the first position. For the second position, you are differentiating with respect to first. You already have a differentiation with respect to x1. Now you are differentiating with respect to x2. Similarly, you have this and so on. Okay. Now for the second column, you will look at this element and take it here. So this will be del square f by del x2 del x1. Okay. And this will be del square f by del x2 square, and so on. You can fill this up. So this matrix is known as the Hessian matrix. And if in machine learning you are working with some simple models, not very deep models, then rather than using gradient descent, you can use better optimization models, which many times will incorporate Hessian matrix also. Okay. So yeah, so we are given with a function. Okay. So we are given f of xy to be this thing, and we want to calculate the Hessian at this point. Okay. So let's construct this matrix. This would be f of xx, f of xy, f of yx, f of yy, right? So let's calculate f of x. This is 3x square minus 2y minus 0, right? F of y is minus 2x minus 6y to the power 5. What is f of xx? This is 6x, right? The second term is constant, so 0. What is f of xy? This is nothing but minus 2, right? What is my f of yx? F of yx, so now I want to differentiate this term with respect to x. So this is just minus 2. Now f of y is minus 30 y to the power 4, right? So if you write it as your matrix, you will get, so put the value also. So 6 into 1 is 6. This point is minus 2. Again this is minus 2, and this is minus 30 into 2 to the power 4 is 16. So this is the value of Hessian that you will obtain. Okay. Okay. So one of the question has this notation. Although this is covered in the lecture, what this notation means, I just wanted to mention. So if you have a notation like del xy by del uv, so you just need to look at the Jacobian kind of a thing. So this is nothing but del x by, so first term, and then again del x by del v, and then this is del y by del u, and del y by del v. But this is not a matrix, but you need to take the determinant of this matrix that you have got. Okay. So this is a change of your variable Jacobian. So you can just calculate it wherever it is required. Okay. So this is what I prepared for today. Any doubts you have, I'm open to it.